Hello everyone. In today's lecture, we will cover another variant of neural networks named recurrent neural networks. In previous weeks, we studied convolutional neural networks for computer vision. As discussed, RNNs apply filters to the input images to generate the feature maps by extracting different features like edges, vertical lines, horizontal lines, etc. Generally speaking, convolutional neural networks provide a suitable framework for processing two-dimensional data such as images. A major characteristic of all convolutional neural networks is that the input data is processed independently. In simple words, RNNs don't consider any state between inputs. Consider input data sets such as text consisting of a sequence of words. Because of this attribute of convolutional neural networks, we must feed the entire sequence to the network at once to process a sequence or a series of words. Today, I want to introduce recurrent neural networks or RNNs, a class of neural networks suitable to deal with sequences of data. An RNN processes sequential data by iterating through its elements and keeps a state containing information relative to what it has seen so far. In other words, RNNs have developed based on the same principle as we are reading sentences. To understand the meaning of a sentence, we process it word by word and memorizing what came before. In other words, RNNs build a new representation of data using past representations and constantly update these representations once new information comes in. This slide presents the structure of a simple RNN. As shown here, it takes as input a sequence of values in forms of time series. The network loops over time steps to process their corresponding data elements in the sequence. Consider this layer processing a data element with time stamp t. The network takes into account the current state of the layer and the input data at time t. It then combines the current state and the input at t to obtain the output at time t. This output will be used in the next layer at time t plus 1. In RNNs, the transformation of inputs and states into outputs is formulated by two weight matrices, W and U. In other words, we should perform two sets of dot product operations to obtain the output of each layer. It should be noted that the input data x in each time step can be a single value or a vector of features. Here I have listed some points related to the recurrent neural networks. As explained in the previous slide, the input data is gradually fed into the network like a time series. It should be mentioned that the number of neurons is the same at every layer. In addition, the number of layers can stretch as the size of input sequence increases. As explained in slide 5, the state value of each node is calculated using two weight matrices W and U, as shown here. In this formula, Ht-1 is the state of layer T-1 and B is a bias. We can use any activation function to add non-linear terms to the model. However, a common choice in these networks is the hyperbolic activation function tanh. In RNNs, neurons play a structural role similar to hidden nodes in traditional neural networks. The nodes in the last layer are also considered as outputs of the RNN. For instance, if a sequence data consists of S time steps, the values returned by the final layer will be the outputs of the network. Here, we have a simple RNN unruled over time. The network is similar to a for loop iterating over time steps to transform the input state t and obtain a new output at time step t plus 1. The transformation is computed using W and U matrices. Each output tensor at time step t contains information about time steps 0 to t in the input sequence. It means that we just need the output obtained in the last layer of the network because it contains information about the entire sequence. By a close look at the RNN diagram, we can conclude that RNNs consist of several layers with identical structure. In fact, simple RNNs are generally too simplistic to learn long-term dependencies in sequences. This characteristic can lead to numerical instabilities, making the training process difficult. To mitigate this problem, more complex networks known as long short-term memory or LSTM networks have been developed. LSTM networks are a more complex variant of simple RNNs. In the following slides, I will explain the structure of LSTM networks and describe how they process sequences of data. In LSTMs, we use the terminology of cell, referring to what we previously called a layer or time stamp. So, LSTM networks consist of several LSTM cells connected sequentially. In the LSTM network, like simple RNN, each cell at any time step takes an input vector and returns the transformed data as output. We have another set of variables C called the cell state or carry. The cell state vector carries information across time steps, preventing older signals from gradually vanishing during processing. The transformation in each cell is obtained based on three weight matrices, WO, UO, and VO. As shown here, a cell output is computed using three dot products with weight matrices, followed by a bias summation and the application of an activation function. In addition, new carry states are obtained by using some dot product operations. We don't elucidate how cell states are computed in this module. The carry states allow past information to be reinjected at a later time, preventing the information vanishing problem. RNNs have shown successful results in natural language analysis and data series processing. For instance, we can take advantage of this network to identify the topic of articles or to do the sentimental analysis of tweets or movies reviews. In the lab, we will practically build and train LSTM networks using Cross API. Chapter 6 in the book Deep Learning with Python covers working with recurrent neural networks for sequence processing. Okay, that brings us to the end of this week's lecture. Thanks for watching this video.